For the biosynthesis of ethanol lab, you'll need an Erlenmeyer flask that contains a rubber stopper, and the rubber stopper is connected to a glass tube that's connected to a rubber hose that's then connected to another glass tube, and that glass tube is in a test tube which will later hold our lime water. So remember to look up the use of lime water in this reaction. Now you'll also have pre-weighed molasses. So you'll need 40 milliliters of molasses, and for this sample the weight is 54.95 grams, but I'll also post that on the Canvas website. We'll also use some yeast as our catalyst for the reaction, and then we have saturated calcium hydroxide, also known as lime water. And then we have a glass stir rod as well. So first, we're going to add the 40 milliliters of molasses to an Erlenmeyer flask. And this is a little tricky because the molasses is pretty dense. It is definitely going to stick to everything. So we need to be somewhat careful adding this to the Erlenmeyer flask. So I'm going to remove the parafilm on top of the beaker, and then I'm just carefully going to add the molasses with my glass stir rod, trying to kind of guide the molasses into the Erlenmeyer flask. Additionally, we need to add 100 milliliters of water to our Erlenmeyer flask. So I'll use the water to help remove the rest of the molasses from my beaker, because as you can see, quite a bit is left over in there. Next, we're going to add some yeast to our Erlenmeyer flask. We need to add about 0.5 grams of yeast, so I'm just going to weigh that out using the balance. So what I'm going to do is zero the weigh boat on the balance, and then I'm going to add 0.5 grams of yeast. This can be approximate. So here I ended up weighing about 0.544 grams of yeast. But you can find that mass on the Canvas website. Now that the yeast is weighed, we're going to add it to our Erlenmeyer flask with the molasses. It did get stuck on my glass stir rod, so I wouldn't recommend leaving your stir rod in there when you pour in the yeast. But I'm just going to gently swirl and mix the yeast into the molasses and water. In the next step, I am going to remove the glass stir rod, and now I'm going to place the rubber stopper into the Erlenmeyer flask. And then the other end of that rubber hose will go into the test tube that is gently resting in another Erlenmeyer flask. But first I'm going to fill that test tube with saturated calcium hydroxide, also known as lime water. And again, remember, you should know the purpose of this lime water, so make sure to read up on that in the lab procedure. And now I'm going to place the other end of this rubber hose into the test tube, make sure everything is sealed tightly, and now we're going to let this sit for 1 week. All right, after 1 week, fermentation should be complete. So now we're going to perform a simple distillation of our product. So in the background, you can see I have a heating mantle with a round bottom flask. There's a condenser, there's a thermometer with a thermometer adapter, a vacuum adapter, and some blue clamps to clamp everything together. So I just transferred the product from my Erlenmeyer flask into the round bottom flask. It's 250 milliliters. And I used a funnel to transfer everything. It was a bit easier that way. But now I'm going to set up my simple distillation apparatus. So first things first, I'm going to add some boiling stones to my round bottom flask. These resist almost all chemicals, so they don't react with your solution. They're ideal for boiling organic liquids and really just preventing superheating and bubbling over. So you only need about 2 to 3 boiling stones, so we'll drop those in. And we can reuse these, so typically what we'll do is try to collect the boiling stones at the end. And we never want to put the boiling stones down the sink. Here is the simple distillation setup, which you've seen in previous labs. So here I have the heating mantle propped up on a platform. I have the universal adapter on top of the round bottom flask. That is then connected to the condenser as well as a thermometer up above. So the condenser is then connected to a vacuum adapter, which is then connected to our receiving flask. So in the next step, we're going to connect the condenser to our water tap in the back. So here you can see I've added the hoses to the condenser. Water is going to come in through the bottom of the condenser and out of the top of the condenser. Now we also can turn on our power supply to the heating mantle. I'm going to start at about 6.5 on the heating mantle. So now we're just waiting for the fermentation mixture to start evaporating. And remember that the vapor should hold some ethanol, and ethanol boils around 78 degrees Celsius. Some water might escape along with the fermentation product, and water typically boils around 100 degrees Celsius. But when ethanol and water mix, they form what's called an azeotrope. And azeotropes have a fixed boiling point, so it can be hard to separate the two. So our product here will really be a mixture of ethanol and water. So I'm starting to notice that the sample is bubbling, so that tells me it's about to boil, and in fact, we should see some of our sample collect in just a bit. I zoomed out here so you can see the temperature rising on the thermometer, and it looks like it's going to settle around 78 degrees Celsius. So that's exactly what we expected for ethanol. And you can also start to see some drips forming at the receiving flask, so that's a good sign. And we'll continue to monitor the temperature as we continue. After a few minutes, I've noticed that the droplet rate has decreased, which tells me that I've collected the majority of my sample, which is again a mixture of ethanol and water. So now I'm going to remove the round bottom flask from the end of my distillation setup, and I will move on to the next step. So here it looks like we have quite a bit of sample. And in the next step, we're going to try to collect fractions of this sample using fractional distillation. And that should help increase the percent of ethanol. So here is our fractional distillation setup. And you can see it's pretty similar to our simple distillation setup, except now we have a fractionating column above the round bottom flask. So the fractionating column just contains some steel wool in the middle of a condenser. So that's going to allow fractions of our sample to collect. And those fractions will likely have different purity levels. So the fractionating column is then connected to the universal adapter, and that is connected to a thermometer up above, which you can't quite see, and also a regular condenser off to the side, which again is connected to a vacuum adapter, and that is resting above our receiving flask. Now I do have multiple flasks off to the side because I'm expecting multiple fractions for my ethanol sample. So we're going to collect all of these different fractions of ethanol, and then we're going to use the density of each fraction, or rather we're going to measure the density of each fraction, and that's going to allow us to determine the purity or the percent ethanol in each fraction. So there's a really large table at the end of your procedure that shows the percent of ethanol which is correlated to the density. All right, so now we're just going to wait for the temperature to increase, and that will tell us that our first fraction is being collected. So I'm starting to see some steam in the bottom of the fractionating column, so that's a good sign. And we'll start to see that steam rising up to the universal adapter. Again, we'll also start to see an increase in temperature. I'm going to fast forward the video so you can really see the steam rising up the column. So as the steam rises up this column, it is allowed to vaporize, recondense, revaporize, recondense multiple times. And this is what allows us to further separate ethanol from water. So hopefully our fraction of ethanol in each sample will be quite high. But again, we're going to collect separate fractions and see which fraction has more ethanol in it. So at this point, I did notice an increase in temperature, and you might see a few drops coming out of the vacuum adapter into the receiving flask. So the temperature range for this first fraction is 65 degrees to about 80 degrees Celsius. And then eventually I'm going to switch out this flask for a different flask. And I do that when I start to notice the drops slowing down. Again, I'm going to fast forward this section of the video so that you don't have to watch the entire sample collection. It took a very long time. So in a bit, we're going to go back to our normal speed, and you'll see that I switch out the flask in a bit. And when I switch out the flask, that will indicate that I've collected my first fraction of ethanol and water. And hopefully it's mostly ethanol. We'll find out later when we measure the density. Now the second flask is going to collect our second fraction, and we'll see how much of that fraction is ethanol later on. So I started to notice that the drips were slowing down, so I changed flasks. I also noticed the temperature rising again. This time I noticed that the temperature was at 81 degrees Celsius. So I have a new flask now, and I'm collecting a different fraction. So this fraction ranged in temperature from 81 degrees Celsius to 91 degrees Celsius. So now I'm going to do the same thing. I'm just going to monitor this fraction, and when the drops start to slow down a bit, I'm going to switch to another flask. So again, I noticed that the drops were slowing down, and the temperature was starting to rise yet again. So I decided to switch out my flask for my third flask, or third fraction here. And the third fraction didn't collect very much product. The temperature ranged from 93 degrees Celsius to 97 degrees Celsius. But again, I really didn't collect much for this third fraction in the beaker, so I decided not to use it at the end of the day. So we'll just skip ahead to the next step. In this last step, we're going to determine the density of each fraction of ethanol. So we're going to need the mass using a balance and the volume using a volumetric pipette. So I have both a 10 milliliter pipette as well as a 5 milliliter pipette, just in case my samples are smaller. And to use a volumetric pipette, I'm going to use this pump, and you want to place it gently on top of the volumetric pipette, and it will hold the pipette by itself. And then to draw solution up, you use the scroll at the top. And then to release your solution into another flask, you use the valve at the side. All right, so I'm going to figure out the volume and mass of my first sample, or my first fraction, and then we'll figure out the density from there. So the volume of my first fraction was 4.40 milliliters. And then I transferred that into a pre-weighed beaker so that I could determine the mass. And remember, density is equal to mass over volume. So you can find the mass and volume information on the assignment page on Canvas. For my second fraction, I only collected about 1.65 milliliters of sample. And then I weighed this fraction as well using a pre-weighed beaker on the balance. So again, you can find this information on the Canvas web page, and you can figure out what the density of this fraction is. And again, you can correlate this with the table on the last page of your procedure and see what the percent of ethanol is for each of those fractions. Good luck!